Welcome back to the course entitled Elementary Electrochemistry. In the previous class, we have discussed about how to determine the conductance of a solution, and from that how to calculate the specific conductance, equivalent conductance, etc. And we had derived some of the expressions related to those physical quantities, and we also discussed about the units of those physical quantities. In today's lecture, I am going to discuss some of the applications of conductance measurement or conductivity measurement, and subsequently in the last week of this course, we will do some demonstrations based on conductance measurements. So today we will start our discussion based on experiments involving conductivity measurement or conductance measurement. So for these experiments, what we need is a conductivity cell which we have drawn in the past, and the cell should have a suitable electrode, normally a platinum electrode of 1 square centimeter area, kept at 1 centimeter apart, and the cell constant is then 1. So the experiments that we want to theoretically understand are these different types of acid-base titrations, B, precipitation titrations, and C, validation of Ostwald's dilution law. So we have already discussed this Ostwald dilution law in one of the earlier lectures, so we will not talk about it in this lecture today. We will concentrate on A and B. These acid-base titrations that we are talking about can be of different types. Number 1, strong acid versus strong base. Number 2, weak acid versus strong base. Number 3, weak acid versus weak base. And number 4, Dibasic weak acid versus strong base. So let us start discussing about the case of strong acid and strong base using the example HCl versus NaOH. So what we know is that HCl being a strong acid, it will remain fully dissociated as H plus Cl minus. So when we add NaOH to this, water is formed and H plus ions are removed continuously. So what do we know about H plus ions? The conductivity of H plus ion is extremely high. So as soon as we start removing the H plus ions from a solution, the conductivity of that solution should tend to decrease. How should that decrease happen? If we try to plot the value of conductance of a given solution with the volume of NaOH added, H plus ions having very high ionic conductivity, the solution initially will have, when no volume of NaOH is added, will have a very high value of conductivity at the beginning. But then with addition of NaOH, this conductivity will decrease very sharply and linearly. And then when all the H plus ions are consumed, that is, the neutralization has taken place, on addition of NaOH solution, this conductivity will slowly rise. So the point at which this transformation happens is your equivalence point. Now, to be able to do this experiment successfully and without incorporating much of error, we need to remember a few things. The point number one and the most important point is the strength of NaOH solution should be 10 to 100 times more than that of HCl solution. Why is that? We all know that conductance lambda depends on concentration of ions, and concentration depends on the number of ions and volume of the solution. So if I suppose have at the beginning, say for example, 10,000 H plus ions in 100 ml solution, during this neutralization to a value of 10 H plus ions in solution, 100 ml solution, I am fine because the volume does not change, so I can easily calculate the change in concentration. But then, while doing so, I am adding NaOH solution. So this 100 ml will not remain 100 ml. If the NaOH solution is of equivalent strength of HCl, so for this neutralization you will need another 100 ml of NaOH. That means the volume will continuously increase, and increase in volume will have effect on change in concentration. Therefore, we should try to make this change in volume as negligible as possible. So suppose if we take 100 ml, 0.001 molar HCl solution, then we should use a 0.1 molar NaOH solution so that the equivalence point will come around 1 ml. So the change in volume of the solution is 1 ml, which is just about 1% of the total volume. So this change can be neglected. Right? So one has to keep this in mind and use a very strong solution of a titrant so that your end point is measured accurately. And as I have shown it up to this for your understanding, but one should do the experiment only up to about this point. If your end point is at 1 ml, one can do this experiment up to 1.5 ml at the most, because then further addition of NaOH further dilutes and the volume increases. As a result, the conductance value becomes incorrect. and you may see that this is no longer a straight line and so on. So with strong acid and strong base, one can expect a graph like this. Hope you are able to understand. The next thing is weak acid versus strong base. Here my weak acid is acetic acid and strong base is NaOH. What happens in case of a weak acid? It stays partially dissociated like this. As a result, the solution without any NaOH addition will not have very high conductivity. So, when we have not added any sodium hydroxide solution, the conductance should be moderate, not like very high, that as was the case with HCl. So now what is happening is, when I am adding NaOH dropwise, that is using a 5 ml burette, and adding drop means 0.02 ml of a solution, which is again 10 to 100 times stronger than acetic acid. This will continuously start removing H plus ions. So as soon as you add the first drop, the conductance will decrease. You add another drop, the conductance tends to still decrease. But then, after addition of every drop, when we try to equilibrate, this dissociation becomes more facile and more H plus ions are generated, hence the conductance will start increasing. So after this initial drop, the conductance of the solution will slowly increase, and near the equivalence point, it will deviate from linearity, and beyond equivalence point it will continuously increase. So this point, which is where the deviation starts, one has to draw a tangent on this line and a tangent on that line. Wherever the two tangents meet will be your equivalence point. Right? So, using acetic acid in the conductivity cell, this experiment when we do, you will see that we do it in a beaker. We take the solution of acid in beaker and insert a conductivity cell where you have the electrodes like this, and the solution goes in between the electrode and you determine the conductance of the solution. So this will be the nature of weak acid versus strong base plot, and I hope you understand the reason for this nature. So now if I try to draw the second one, weak acid versus weak base. Suppose acetic acid versus ammonium hydroxide. You know that it is very difficult to do this kind of titrations using an indicator, because no indicator is suitable for this weak acid versus weak base estimations. So it is best done using the conductivity measurement. So now I want you to think about what should be the nature of this conductance versus volume of NH4OH plot. See, initially what is happening? We have acetic acid as dissociated like acetate and H plus ions. So we will have a moderate conductivity somewhere here with zero volume of ammonium hydroxide. Then initially the conductance will fall and then it will slowly increase, and beyond the equivalence point, what was happening here will not happen there, because I was adding NOH, which immediately it is already dissociated and it increases the conductance of the solution significantly. So there was an increase in conductivity. Whereas NH4OH is not a strong electrolyte, it is again a weak electrolyte, so the conductivity will go like this. So what is happening here is, now we need to draw a tangent here, we need to draw another tangent there. Wherever the two tangents meet, that will be your equivalence point of this particular titration of weak acid versus weak base. Is that clear? This portion is same as that, and the right hand side portion, where after the equivalence point it slowly decreases because ammonium hydroxide is a weak electrolyte and we are adding more and more ammonium hydroxide, means the volume of the solution is increasing, and as a result the concentration is decreasing, hence the conductance is going to decrease. So this is what will happen with strong acid and weak acid and weak base combination. So I want to give you a homework. Think about what will be the plot of a mixture of HCl and acetic acid titrated with NaOH solution. So this you should think and try to draw yourself, and you can write to me, we can discuss about this over email. Similarly, I think I should give you this example, this thing also, that if it is HCl plus acetic acid done with ammonium hydroxide, what will be the nature of these two titrations? What do you think will happen in case of 4, the case of weak dibasic acid versus NaOH? Say for example, oxalic acid versus NaOH. If you remember the experiment of this using potentiometry, we could see the dissociation of acetic acid 2 times and we could determine the pK for the 2 acids. In this case, what will happen is not going to be very sharp. So you see, both the acids are weak. So the neutralization, when it happens, it will not be very prominent or sharp. So initially it will decrease, then it will go on slowly increasing. After the first neutralization has taken place, the curve will bend little bit, and then when it is over with NaOH, it will go up. So if you get a graph like this, if you get a plot like this, I think I should write volume of NaOH here, and it is 0 volume of NaOH. What one has to do is, one has to draw a tangent here, one has to draw a tangent there, and one has to draw a third tangent here. So this one will indicate the first equivalence point, this one will indicate the second equivalence point. But these changes will not be very prominent or very sharp, so it is not advisable to do this kind of titrations using conductometric method. Rather, one should try to do this using a potentiometric method that we have already discussed. The next type of conductometric titration is the conductometric precipitation titrations. In case of a conductometric precipitation titration, one has to choose the pair of compounds very precisely or with lot of consideration. Depending on the speeds of those ions, the plots will become different. So I am giving you one example of KCl versus HNO3. So, as you know, KCl is used as a standard solution for determination of cell constant of a conductivity cell, and it is very easy to handle KCl as it is not hygroscopic and is free flowing salt. So, one can use KCl as a standard for this type of experiments. So, I am trying to determine the concentration of either unknown AgNO3 or unknown KCl, depending on whatever you want to measure. Only thing one needs to remember that we are taking KCl in a beaker. So the concentration of KCl should be low, maybe 0.01 molar, and the concentration of silver nitrate should be high, that is either 0.1 molar or even just 1 molar, right? So now when we have not added any silver nitrate, it will have a decent conductance, and then when we slowly start adding silver nitrate, what will happen? KCl plus AgNO3, we will get AgCl as precipitate and KNO3 will form. So the ion that is present K plus still remains. Chloride gets precipitated, silver gets precipitated, nitrate is coming. That means in your solution which had K plus plus Cl minus, after the experiment, Cl minus ions are replaced by NO3 minus ions, keeping the concentration of K plus same. Now, if you look at the table for the transport numbers or the ionic conductivity of these two ions, chloride and nitrate, you will see that the ionic conductance of chloride and nitrate are about the same. So what will happen is, while adding the silver nitrate dropwise, there won't be much change in the conductance. But then when all the chloride is precipitated and no more silver chloride gets precipitated, if you are continuing to add silver nitrate beyond that point, the conductance of the solution will continuously increase. So this sharp end point will be giving you the equivalence point. The point where the straight line changes its slope will then give you the concentration of KCl solution. One can use KCl solution as standard and determine silver nitrate unknown. In that case, one has to take silver nitrate in the beaker and add a 10 times or 100 times stronger KCl solution from burette, and you remember we should use a 5 ml micro burette and use 0.02 ml KCl solution or silver nitrate solution at a time. So the value for L0Cl minus is about the same as L0NO3 minus, and hence you will get this kind of plot. If you take two different ions, say for example SO4 2 minus and what I am trying to say that if it is K2SO4 versus barium nitrate, then you are trying to compare sulfate with nitrate. So depending on the corresponding values of these two L0s, the nature of the graph will change. Here sulfate is getting replaced by nitrate. If nitrate has larger L0 value, so the conductance will continuously increase. If nitrate has a lower L0 value than sulfate, the conductance will decrease. So you will have to think and replot this graph for this kind of precipitation titrations. So I am giving you another homework. If I give you a mixture of HCl plus NH4Cl plus KCl in a mixture, each of the order n by 30, I want to know the individual concentrations of HCl, NH4Cl and KCl. This is about n by 30. These are all made approximately, and then I want to know the exact concentrations of chloride, concentrations of HCl, ammonium chloride and potassium chloride in this solution using a conductometric titrations. So this is a homework for all of you. So try to solve these problems. You try to draw the graphs. We will probably discuss this in the next lecture. Thank you.